us take the second equation. What was second equation? It was fz minus mg theta sine theta 1 is equal to m w dot minus q u1. Please remember, we have taken stability axis system, right? And I'll repeat what is the stability axis system is this. So this is the airplane, this is your x, originally x is this, y is this, and z is this. And here is the velocity vector like this. This is a normal body phase axis system. If I'm talking about stability axis system, then what happens? This airplane is this, CG, and this is velocity vector. So I align x-axis like this, and we call it xs, and this becomes zs stability axis. Okay, so this becomes alpha. So I am keeping the x-axis aligned to the velocity vector. Why? Because then there is no component of velocity in z direction. So w1 becomes 0. w1 goes to 0. But here you see w1 not equal to 0, because this is the velocity vector. There will be a component along z direction. But here, by choosing stability axis system, w1 becomes 0. So that after applying this, only we got this final equation. You should not forget, right? Extremely important. And why stability axis system? Because we know if velocity is in this direction, then lift perpendicular to this, drag is opposing to this. So the computation becomes simpler. Again, we'll go mechanically like the way we have done there. So we'll write fz is now, we are smarter. We'll write u by u1, then alpha, putting a term q, we may put a term alpha dot, and delta E. You might have seen in FX modeling, we haven't put q and we haven't put alpha dot. Theoretically, they should be there, but they are so small, so we have neglected it, right? For fz, we need to know that why there should be a q, which you know very well, that if this is the CG, and if there is a horizontal tail or a wing, whatever it is, if there is a q, then this q, if it's going up like this, so the tail is going down, so relative air is going up like this, and it's moving forward, so there will be a delta alpha, which is q LT by u1, right? I say LT is distance between aerodynamic center. So this delta alpha will give you indeed a force in terms of lift, and depending upon what is your z-axis, this will have a component along z-axis, right? So that is why q will play important role in fz, and soon you see it will have a most crucial role in terms of moment, pitching moment. You'll also see that alpha dot will play a role, and we'll come back to the physical significance of alpha dot in developing forces, or fz, when we talk about the derivative with respect to alpha dot. And delta you know very well, right? Because of delta there will be a force lift, and that will have a component along z. So that modeling is okay. Now this part will be almost mechanical, you'll see, since we have done the first problem so exhaustively. So I can write fz as dfza by du by u1 into u by u1 plus dfza by d alpha into alpha plus dfza by dqc by 2u1. Let me write, and I'll tell you. And dfza by d alpha dot c by 2u1 into alpha dot c by 2u1 and plus dfza by d delta E into delta E. You could see these two, alpha dot c and qc by 2u1. Remember, we have to convert u into non-dimensional by dividing it by u1, because we wanted all this thing should be in non-dimensional form. But you could see here, this q and alpha dot have a time dimension, right, radians per second. So what we do is, now we write fz as a function of u by u1, then alpha, non-dimensional. For q, we write qc by 2u1, and you know that QC by 2U1 is non-dimensional. Then for alpha dot, we write alpha dot C by 2U1, right? Then delta E. So it is the same theory, same understanding that we need to keep this argument non-dimensional. So for U, we make it to U by U1. So for Q, it's a conventional thing, QC by 2U1. Somebody asks why 2. So it's take it as a convention, QC by 2U1, as long as dimensions are dimensionless. Okay, so if I write like this, now from here, I can write dfza by du by U1 into U by U1, dfz by d alpha into alpha, dfz by QC by 2U1, QC by 2U1, and dfza by d alpha dot C by 2U1, then dfza by d delta E into delta E. Correct? So what is now? What is important now? Important is, can I get quick estimate or formulation to evaluate these derivatives at steady state? That is the catch point, at steady state. Let's first attack dfza by du by U1. Before we start doing it, we know Fz means aerodynamic perturbed force along z direction. Okay? So let us do that. So I can write Fza is equal to minus Cl into half rho U1 plus U whole square S. What is this? This I am trying to find out dfza by du by U1. If you recall, this is the aircraft, this is U1, and some because of perturbation, this is U. The total speed is U1 plus U. So what will be the total force? Will be half rho V square, which is U1 plus U, S into Cl, right? So now what I do, I write Fza is equal to minus Cl into half rho U1 square S into 1 plus U by U1 square. No problem? 1 plus U by U1, yes, square, fine. So now I am to find out dfza by du by U1. So do that. So first I do like this, let's say minus Q infinity S, this is half rho V S, and then Cl, and then derivative of this, so that will be 2 into 1 plus U by U1, right? Then second is minus Q infinity S, 1 plus U by U1 square into dCl by du by U1. No objection, class 10th. So now I put condition at steady state. When I say at steady state, what does it mean? I mean the perturbed quantity should be 0. So this becomes minus Q1S Cl1 into 2. See, this will become 0. So minus Q1 S into this is 0. So this goes into dCl by du by U1. So what is the final expression? Final expression is as simple as dfza by du by U1 equal to minus Q1S, 2 I can put here, or I can put outside, 2Cl1 plus Clu. So you could see dfz by du1 is as simple as this. Let us see how many things we understand. What is Q1? Q1 is the dynamic pressure at steady state. If it is a cruise, it is half rho V cruise square. Cl1 is, at cruise, Cl1 will be 2W by S rho V cruise square. That is lift equal to weight. What is Clu? Let us understand this. What is Clu? This is important. Let us focus on Clu. And by definition, it is dCl by du by U1. Right? Remember, we have already done something CdU. Okay? So let us see here. If I plot Cl versus Mach number, you will find the plot will go something like, again 0.6 to 0.7 constant, and it goes, there's a dip at transonic and goes like this. Okay, could you see this? If I darken it, it goes like this, roughly like this. And this point is in and around 1. It could be 0.98, it could be 1.2, depending upon the shape, no shape typically. Now, if I see here, if I try to tell you what is the dCl by dm up to 0.6 or 0.7, again, this is 0. But for region 1, it is dCl by dm is positive for region 1, and dCl by dm is less than 0 for region 2. Right? At supersonic speed, dCl by dm is less than 0. And at subsonic and up to 0.6, 0.7, dCl by dm is almost 0. And between 0.6 to 1.1 or 1.2, around this region, the slope tries to remain positive. Okay? This, once you understand this, we'll try to interpret CLU. So this dCl by du by u1, I can write as dCl by du by a. We are trying to investigate and understand dCl by du by u1, which I can write dCl by u by a, where a is of course velocity of sound, right? Okay. And I presume that you understand Mach number is velocity of vehicle by velocity of sound, right? Mach number. So this I can write as m1 into dCl by dm. See, this is CDU. Equivalently, I can see this through this expression. It's not CDU, sorry, CLU. This is CLU, okay? Right? CLU. I can divide by A, so I get M1 dCl by dm is CLU. So now, just now I showed you a representative of CL versus Mach number, and which is almost like this, right? Okay? And you know that up to 0.6, 0.7, this dCl by dm is 0. So CLU will be 0. CLU will be 0 up to 0.6 Mach or 0.7 Mach. Then CLU will be positive up to, say, from 0.6 to 1.0, and CLU will be negative at high supersonic speed. It's extremely important. So that is what is CLU. So you could see that as we are going to apply this for a high speed, how these derivatives will play important role. It will just change its sign from subsonic to supersonic, okay, or high subsonic to supersonic. So we have understood what is dFZA by du by du1. So now we'll do dFZA by d alpha. Okay, what is this? If you recall, see, when we draw this diagram to calculate dFXA by d alpha, so this is alpha, right? This is CL, and here is CD, and of course this is alpha. So I can write FZA is equal to, you see that Z direction is downwards, so FZ I can write as minus D sine alpha minus L cos alpha, right? Or if I don't write CD, I write drag, you will understand better. So on the Z is vertically down, so what will happen? Let me write this X. What will happen? L cos alpha will come here, L cos alpha, which is in the opposite direction of Z. So minus L cos alpha. Similarly for D, you could see one component here, one component upward. So this is D sine alpha. Again, it's upward direction. So it's minus D sine alpha. As simple as that. Right? So this I can write as FZA as minus Q infinity S, right? CD sine alpha plus CL cos alpha. What are these alpha? Alpha are the perturbed angle of attack. Do not forget this. Alpha is the perturbed angle of attack. Okay, this is fine. So now what is our aim? Our aim is to dfza by d alpha will be what? Will be minus q infinity s, right, into CL alpha plus CD 1. And I put it 1, and I expect you should be able to derive this relationship. This class 10th problem, you have to take derivative, one derivative with respect to CD, one derivative with respect to the sine alpha, like that, and put at steady state, alpha perturb is 0, so you should get dfza by d alpha, dfza by d alpha as minus q1s into CL alpha plus CD1. Correct? Yes. Okay? Any problem? You should not have any problem. Let's be very point blank. You have to put an effort. Simply class 10th or 11th, you take a derivative, put alpha equal to 0, you will get this answer. Right? Okay? So this part is also taken care. Now we'll talk about the third term, dfza by d qc by 2u1. Right? Let us understand what is this. What is Q? Q is the perturbed pitch rate, right? Now think of this airplane. This is the tail, this is the wing, and let's say here is the CG. If there is a Q, that's vertical tail. You know the Q is the perturbed pitch rate. So as this airplane goes for a Q, then there is a Q into LT, relative airspeed, I put it at aerodynamic center. And since this is the LT tail moment term, I can write delta alpha is Q LT by U1. And if you want to take moment, then I'll take help of LT. If this is the delta alpha, then what is the delta lift? Delta lift will be half rho V square at tail, S tail, CL alpha tail into delta alpha, which is Q LT by U1. So what is delta CL? We know that for delta CL I have to divide it by half rho V square free stream. So this will be neta into ST by SW CL alpha tail into Q LT by U1. Now it is interesting to see that we will find out CLQ. You know what is CL alpha? CL alpha is dCl by d alpha. Alpha is non-dimensional. We will now write CLQ, which is dCl by dQ C by 2U1. Because Q is a dimensional quantity, so QC by 2U1 is non-dimensional. So we will define CLQ as dCl by dQC by 2U1. Okay? No problem on that. So since delta CL is this, so CLQ for a linear part I can write delta CL by Q C by 2U1. That will be neta ST by SW CL alpha tail into Q LT by U1 divided by Q C by 2U1. So what do you get? Q get cancelled, U1 will get cancelled. So CLQ is nothing but neta ST by S wing or S reference CL alpha tail LT by C, and some two term will come here because of this two, right? So this is the CLQ. Okay, so if the airplane is rotating like this, then the force will be in the upward direction, so it will be in the opposite of Z direction, right? Clear? If I want to use this expression in the Z direction, then it will be negative. That is how we write now the CLQ. If Q is positive, then CLQ, as far as sign we have seen, it is greater than 0, because this lift force will be upward, right? as it is going down. You will see that if this is the tail, as q is positive like this, relative air is coming like this, angular momentum is increasing, the force is in the lift direction, but which is opposite to z direction. So we will write Fz because of q is minus half rho v square s into CLQ into QC by 2U1. Is it clear? Fz is half rho v square into CLQ into QC by 2U1, because this part complete is CL due to Q, that is dCl by dQ into QC by 2U1. When I write CLQ, that means it is dCl by dQC by 2U1. So naturally, dFZA by dq c by 2u1, it is simply equal to minus q1s CLQ. As simple as that. So this term is so straightforward. This term, this is equal to minus q1s CLQ. Now we have here, this term is also simple. I can write FZA, right? Again, you see, if this is the tail and this is the elevator, if delta E is positive, right, that will give a force in the upward direction lift, which is again opposite to z direction. So I have to write FZA as minus half rho v square S CL delta E into delta E. Because this is the CL because of delta E, minus sign because delta is positive. If it is down, the lift is in the opposite direction of Z. So this minus sign. So what is your dFZA by d delta E? This is nothing but minus Q1S CL delta E. And you know very well how to calculate CL delta E, and you know that expression we have already done. The CL delta E, you can check your notes in the control part. CL delta E is CL alpha tail into tau into neta into ST by S reference. Okay, you can cross check. Let's come back to this. To know what is the Fz, I needed to know these derivatives. Today you have finished this, and this. What is left is alpha dot derivative, right? We will take a separate class on alpha dot, and we'll try to understand.